All right, we're going to move on to the last couple things, which are going to be graphing and then domain, and those ideas definitely tie together really well. And that'll be the wrap up for this video. So let's move on. So when we get to talking about graphing, we want to stick with that idea of inverse, right? How they're related. That'll help you definitely graph a log graph. And then, of course, eventually you want to not have to do a conversion or always think about what's the exponential sort of equivalent idea, but it's good to start that way. And we already talked about the asymptote concept, how we got a horizontal for exponential and a vertical for logarithmic. Domain and range-wise, I didn't hit that earlier, but domain for a exponential is all real numbers. In other words, you can put in whatever you want as an exponent. Range-wise, we know no graph sits down here, so 0 to infinity. If we do the inverse concept, then we know that the inverse is definitely the switch of domain and range, so switching x and y. And the reason this domain is what it is, besides just being the inverse concept, is throw in that vertical asymptote for a second and check out your graph. There is no logarithmic graph over here. And the reason being, we'll get to that in a minute. We're getting close to talking about that. I want to actually show you guys a graph, and we'll discuss that in a sec. Same thing with a natural log, right? So we switch domain and range, because those graphs are basically the same idea. Okay, and now we're going to do an x-intercept instead of a y-intercept. We'll have that vertical asymptote instead of a horizontal asymptote. I think the best way to show you is just doing some actual graphs, so let's jump into some graphs. What I'm doing here first is, here's what we want to graph. So we're talking about a graph that has transformations. If we're clipping through the transformations, we got a right, we got a down, we got a reflection over the x-axis, all those things going on. What I want to do is kind of progress from exponential to kind of a no transformation type graph, then to the transformation. And as we start thinking about this, a good way to go would be, I guess, think about its inverse and say, well, I could just switch the coordinates, right? So I said good exponential choices 0 and 1 because they produce 1 in the base. What are good logarithmic choices? Well, let's put in the actual coordinate switch and talk about why you might choose these numbers. So I put in the coordinate switch idea. There's the inverse concept. So if you log base anything of 1, a property, you get 0. And if you log base any number of the same number, you get 1. So when you start talking about what do I choose for x's for log graphs, always choose 1 in the base. They're definitely your best choices. And then we can start talking about, okay, what's this graph look like when we do the transformations? What you want to try to do is not have to do this for sure every time you do a log graph. You just want to be able to start with, hey, 1 in the base, 1 in the base. Okay. So I'm going to put in 1 in the base. So 1 and 0 and 3 and 1, and then we're going to start to work through our changes here. I visualize this is my log base 3 of x, no transformations. Then I'm going to start to do the transformation. So that x as a reflection would stay put. This one would now move down here. So what I'm going to do is that reflection first. And the order that I like to do things in when we talk about doing transformations from other chapters is always reflection first. I think it's just easier to visualize. So I'm going to take this one back up for a sec. This would have been my graph. No transformations. Then my reflection. And that's counting, right? So now I'm going to go 2 to the right, down 1. And there's a coordinate there. Just happens to hit that same spot, right? But 2 to the right, down 1, and 2 to the right, down 1. Now again, if I'm kind of working through the visualization part of it, here's no reflection. Here's reflection, and then there's finally a shift. And also what you want to make sure you do is don't forget to shift your asymptote along with the graph. So while it would have been sitting here with no transformation, now it's sitting over here somewhere. There we go. And then sketch your graph. So again, visual one more time. No reflection. Drop that x down. Reflection. Shift it. Now, just for a second, sidestep here, a discussion about why the graph is where it is. Some things that you can't do logarithmically, for the same reason you can't do them exponentially, is you can't log any base of 0 and produce a number, because you'd have to be saying then 3 to the what is 0. No answer to that question. You can't log any base of a negative number and produce a number, a real answer, because for the same reason exponentially, 3 to the question mark equals negative. That can't happen. So what you want to get to know right away is you can't log 0, you can't log negative, and for that reason, no graph sits over here, unless you would reflect it over the y-axis. But outside of that one exception, no graph over here because these things are not possible. Final domain, 2 to infinity, your range will be an automatic, always all real numbers. So again, where is their graph to the right of my asymptote? Natural log work out the same way. Again, I would choose 1 in the base. So in this case, 1 and e as my way to evaluate. So 1 in the base because 1 produces 0. So the ln of 1 is 0. And the ln of e is 1. And then again, start with kind of the basic idea of, no transformation and a little bit of shifting. So I'll pop those up quick. Now when I go to do e, I've got to do 2.7. Excuse me, do the best I can. My asymptote, my original asymptote would be sitting here. I don't think I've got that in there, but when I go to shift left 3, so let's pop up the asymptote, so we're there. So no reflection on this one. There's my basic natural log coordinates, and just move them. It's easy enough, it's counting, right? So we're going to go left 3, and then up 2. And then this one, you got to do a little bit of, do the best you can with the counting of the 2.7, but about there. And then draw your graph. So I don't think log graphs are particularly complicated. I mean, they're pretty simple, like an exponential. The thing you guys will maybe have an issue with is once you have done both, that you start blending the ideas together. You got to really watch out for that. Like you kind of mix the asymptotes, or you start mixing, or people do stuff like that. And of course, I would be doing like that. Like, what are you doing? You just drew right through the asymptote, right? But your brain's kind of thinking like an exponential graph, but you got a logarithmic asymptote, and you just got to get those things straight, which you will. Just a little bit of practice there. Okay. And then domain and range. And then for this one, actually that's a copy and paste error there. This would be -3 to infinity. Okay. Last little bit of this is talk about domain, and we're going to sort of build up the idea without a graph and then actually multiple logs, and how do you deal with that? So without a graph, what I should know now is that graph always sits to the right of my asymptote minus a reflection. So if my asymptote's right 5, then it's 5 to infinity. There's your reflection. So that puts it on the other side, the left side of the asymptote. So now you're going to go negative infinity to 0, as opposed to 0 to infinity. But what if you insert multiple logs into the problem? What does that do? And when you insert multiple logs, you now have to do like a domino type effect. Like how does the inner log affect the outer log, which affects the overall domain? When I try to reason out problems like this, what I always do is start with what is the outermost log's domain issue, which is the standard domain issue. So standard domain for any basic log function is 0 to infinity. And then when I move to the inner log, what I ask myself is, what number here would cause me to get this number? In this case, that'd be 1. So if you log base 10 of 1, or log base anything of 1, you get 0. Which means in this equation, you'd have to go 1 to infinity. And here's how this works now. So if I say 1 to infinity, why is it 1 and not 0? Because 1 plugged in here would cause this to become 0, and then log base 4 of 0 would be the original domain issue. Can't log 0. Then expand this idea to more logs, and there's more kind of domino effect you got to think about. And the first time you do this, it's a little bit confusing, actually, I think. So I'm trying to map it out for you guys. But what if we do multiple? Now we got 3, we could do 4, we could do as many as we want. So start about thinking of it this way. What value of x in the inner function produces the domain issue of the outer function, and work it that way. So I'm going to start with a string of thoughts. What is the outermost log's domain issue, which is the standard domain issue? 0 to infinity. And then I say, next go 1 log in and go, now what here would cause me to get 0? Well, we just did that a minute ago, that would be 1. So log base 10 of 1 would produce the 0 result. Well, now it's 1 to infinity. Now go to your innermost log. What number here would cause you to get the 1? And that would actually be the same as the base. Now we're 7 to infinity. So in a chain, if you start with where x actually sits and you plug in 7, 7 here causes 1 here, causes 0 here, causes the ultimate domain issue. So 7 to infinity. And then, like I said, what if you add in another log? Or multiple right after that? Same question. So now you're saying what number here would cause you to get to 7? And that actually would be 3 to the 7th. So log base 3 of 3 to the 7th is 7. Now it would be 3 to the 7th to infinity. We could do this forever. We probably won't do much more than 3 or 4. But it's a chain of thinking, and what you always got to do is say when this number gets plugged in, which is this one I should say, it has a domino effect going backwards. So if I put in 3 to the 7th, I get 7. That causes 1. That causes 0. That causes the ultimate domain issue. Okay. So it's kind of a little bit of a logic problem, but a good one I think for you guys to work through and see how that chain works. Last two problems are going to be finding inverses. So this is also kind of this one's a little bit of a chain. It's an undoing. We're going to go switch the x and y, right? Solve for y. And how we solve for y is a little bit weird here. But remember, this is our y value, so we're going to switch the two. So there's the switch of x and y. And then start rewriting exponential one log at a time. So in this case, we have to go, let me pop it up here. We start with the rewrite, which goes base to the exponent equals number. So that's 4 to the x equals, then go again, base 10 to the exponent equals number, then go again, base to the exponent equals number, and that actually is your inverse. And they're going to look, again, kind of funky, but it's a series of rewrites. Kind of weird, but that's how it works. And hey, you've got it. I mean, you've got an exponential equation. It's the inverse of the log. Last one is to go the other way. Let's do the inverse of the exponential, come up with a log equation. Switch your x and y. Now we've done this process. The next couple steps we've done. Multiply both sides by the denominator. Distribute your x in. If we're going to solve for y, we should group our y terms to get them together on the same side. Remember how we get 2 down to 1? You factor it out. Isolate that. Divide both sides by. Now this is still exponential. And remember that the inverse of an exponential is log. So now comes the rewrite. Rewrite it logarithmically. So y. So if I do it in words, log base, so log base 3, number equals exponent. Exponential, logarithmic. Okay, and that's going to wrap it up for our 2 videos on the reintroduction to logs. I'm sorry there's 2 and it's a little bit longer, but the first topic of first day of talking about logs or section, it's a little bit much to kind of throw at you guys. It gets better as we go further and further through the chapter.